So in this video we're going to derive what's called the law of sines. And the big idea for the law of sines is that we have so far defined everything in the realm of trigonometry using right triangles, or triangles that have a 90-degree angle for one of the three angles. So the issue is going to be, what do you do when you run into an oblique triangle, a triangle that is not a 90-degree triangle? And what we want to do is develop some tools that will help us to solve oblique triangles, triangles that are not solvable using right triangle trigonometry techniques directly. So oblique triangles are going to show up in two main flavors for us. They're going to show up as acute triangles, A-Q-U-T-E. So those are triangles like the one that you see here, where all three angles are less than 90 degrees. And the other possibility is we can have the family of triangles called obtuse triangles, where one of the three angles is greater than 90 degrees. And so for the law of sines to come up with it, what you need to do is address both of those situations. So in this particular case, I have a triangle here that I've replicated here. So these are exactly the same triangle. This one is just a copy of this. And the way that you derive the law of sines for an acute triangle is you go ahead and label in the angles. So I'm going to call this angle A, I'm going to call this angle B, and I'm going to call this angle here angle C. And the convention in geometry is, if you're using English letters, to use capital letters for the angles, and then the side opposite the angle, you label it using a lowercase letter. So if this is big A angle, this is going to be lowercase side length right here, A, lowercase a. So A and the side opposite of A, angle B and the side opposite of B is going to be lowercase b, and angle C, the side opposite, will be lowercase c. And to derive the law of sines, what we do is we go to any of the three angles, it doesn't matter which one, and we drop a perpendicular from that angle to the other side of the triangle, so that we get two right triangles. And then we apply right triangle trigonometry to come up with some relationships. So for example, the angle A, the sine of angle A, we know is the side opposite. So if I give this side right here a name, let's call him height 1, I know that the sine of A will be equal to height 1 over the hypotenuse. So it's opposite over hypotenuse, and the hypotenuse is going to be length C. And then I could multiply both sides by length C. And if I do that, I get that C times sine A. C times sine A is just equal to height 1. And then for angle C right here, what I see is that the sine of angle C is equal to opposite, which is this height 1, over hypotenuse, which is length A. Multiply both sides by A, and I get that height 1 is equal to A times the sine of C. So if A sine C is height 1 and C sine A is height 1, by the transitive property of equality, I know that C times sine A has to be equal to A times the sine of C. And then we just take and divide both sides by A times C. And we get C divided by C is 1, and A divided by A is 1. So we wind up discovering that the sine of angle A over the length A is equal to the sine of angle C divided by the length of C. Now we go to the triangle again, and we drop a perpendicular from either of the other two angles over to the other side. So we'll get a clean picture here. A, B, C. This is B, C, A. Grab either of the other two angles and drop a perpendicular from that angle to the side opposite, so that we have two right triangles again. And we'll label this height h2. And then what we can see is that the sine of b is going to be equal to opposite angle b, which is height 2 by right triangle trig definitions, over the hypotenuse, which is length c. Multiply both sides by c, and we'll get c sine b is height 2. And then we step over to angle c and play the same game. We go sine of c is equal to the side opposite, which is height 2, over the hypotenuse of this right triangle right here, which is length b. Multiply both sides by b, and we'll get b divided by b is 1, and we get b sine c is height 2, and c sine b is height 2, so they must be equal to each other by the transitive property of equality. So a sine b equals b sine angle c, and then we divide both sides by, oop, that's a c right there, making mistakes. Always making mistakes. That's just to show we're human, right? This is a c, so this is a c, and then we'll multiply both sides, divide both sides by bc, so we get c divided by c is just a 1, and we get over here b divided by b is just a 1. So sine b over side length b equals sine c over side length c, and we see that this guy here shows up in both equalities, which means by the transitive property we can stitch everything together. If sine a over a is sine c over c, and sine b over b is sine c over c, then all three ratios are equal to each other. And this relationship here is the law of sines. So that demonstrates or derives the law of sines for the acute triangle case. So here's the law of sines, have it summarized, but what we haven't done is derive it for the case where we have an obtuse angle, an angle that's greater than 90 degrees. So for the obtuse case, you would step in again and label your angles A, B, C, and opposite A would be side length A, opposite B is side length B, and opposite angle C is side length C. And for the obtuse angle, you grab the obtuse angle and you do exactly what you did on the previous slide. You just drop a perpendicular to the opposite side so that you construct two right triangles, and then we use right triangle trigonometry to set up some relationships. So I need to label this height, give it a name, call them height 1. And then what we see is that the sine of angle C right here, so the sine of angle C is going to equal height 1 over, that's the side opposite C, over the hypotenuse, which is length B. Multiply both sides by B, and we get B times the sine of C is height 1. And then we go over to angle B and do the same thing. He's got a right triangle right here. So we say, hey, I noticed that the sine of angle B is equal to the side opposite, which is height 1. So this is equal to height 1 over the hypotenuse of this right triangle has length C. Multiply both sides by C. So this plays out exactly the same as it did on the previous slide. And then we set the two equal to each other. We manipulate like we did before. B sine C equals C sine of B. We divide by C times B. Divide by C times B on both sides. C divided by C is 1. B divided by B is 1. And we get our first relationship. So the rub comes once we've dealt with the obtuse angle, is that we try to drop a perpendicular to the side opposite from either of the other two angles. The situation is that the perpendicular falls out, it falls on the sideline of this triangle outside, or on it falls on the exterior of the triangle. So drop a perpendicular from here to the line between angle A and C, the side line. It's going to hit outside the triangle, and that's the rub. So we're going to give this height a name. We call it height 2. And if this is angle A right here, right, then this angle, because I have a straight angle right here, 180 degree angle, this angle right here is going to be 180 degrees minus angle A. And what I see from this is that the sine of this angle, which is 180 degrees minus A, is equal to the side opposite that angle, which is height 2, over the hypotenuse of this right triangle, which is side length C. So I get this relationship. And I can come over here to angle C, and what I can see is that the sine of angle C is going to be equal to, he's on this big right triangle right here. So the side opposite C is actually also H2, but his hypotenuse is the side length A. And I can multiply both sides by A. A divided by A is 1. So we get A times the sine of C is height 2. But this, I've got some work to do. And the key is to recognize that I can use the difference identity for sine to rewrite this. So if I rewrite this using the difference identity for sine, I'm going to get sine of the first angle. So sine of 180 degrees times the cosine of the second angle. So cosine of A. And then it's a minus, so I'm going to get a minus, and then it's going to be the cosine of the first angle, so cosine of 180 degrees, times the sine of the second angle, which is A, and this difference has to still equal the ratio H2 over side length C. And the sine of 180 degrees, we want to remember from the unit circle, if we're in the 180 degree position, then we're over here at -1, 0. So the sine is going to be 0. So we get 0 times cosine of A minus the cosine of 180 is -1 times the sine of A. And this has to equal the ratio H2 over C. So we get 0. Double negation is a plus. 0 plus 1 times sine A is just sine A equals H2 over C. We multiply both sides by C, and we get C sine A equals H2, A sine C equals H2. We set them equal to each other, so we say A sine angle C has to equal C sine angle A. And then we play the same game that we've been playing. We divide both sides by A times C. A divided by A is 1, C divided by C is 1. And we get sine C over C equals sine A over A. So we get to tag everything in, sine A over A, and we get the law of sines either way.